If you need to learn how to assign R and S to chiral centers, you're in the right place. I'm going to show you how to do this easily on any line bond structure. In this video, we're going to cover how to assign the R and S to chiral centers using the CIP priority system. CIP stands for Kahn, Ingold, and Prelog, and these are the three people that came up with this naming system. The video is going to be broken into three major parts. First, I'm just going to give a quick overview of what this CIP priority system concept is all about. Then, we're going to take a look at how to assign the R and S regardless of where the lowest priority group ends up being situated. And then last, we're going to take actual molecules, and I'm going to teach you how to assign priorities 1, 2, 3, and 4, so we can assign the R and S to a bunch of different structures. Part of understanding stereochemistry is recognizing that we have two different ways that four different groups can attach to a chiral center. These two different ways are called the absolute configurations, and the CIP rules give us a way to distinguish one of them from the other. Okay, so let's talk about what CIP system is all about. Here's a molecule with a chiral center. We have our four different groups coming out of the carbon. What we're going to be doing is assigning priorities 1, 2, 3, and 4, where 1 represents what we call the highest priority, and 4 will represent the lowest priority. We're going to be staring into the chiral center, and the idea is that we want number 4, the lowest priority group, to be projecting away from our vision. That means that the other three groups are going to be sticking out in a way very similar to the Newman projection. Those three are going to have the 1, 2, and 3 assigned to it. And from here, what we do is we look at the direction of travel of 1, 2, and 3. In this case, 1, 2, and 3 is traveling to the right. It's traveling clockwise. When 1, 2, and 3 travels clockwise like this, we call this letter R. This is from a Latin word rectus, which loosely translates to right. Of course, we could also be staring into the chiral center with number 4 on the back and have the 1, 2, and 3 traveling counterclockwise or traveling to the left like this is showing. When 1, 2, and 3 is going to the left, we end up calling this letter S. And S is from the Latin word sinister, which loosely translates to left. So this is an overview of what the system is all about. Okay, we just talked about the CIP rules and how it relies on number 4 being in the back. But after you assign your 1, 2, 3, and 4, number 4 could end up in one of 3 places. So we have to know what to do in each of those situations. Here's number 4 ending up on the dash. That's what we just talked about. But number 4 could end up on the wedge like this. Or number 4 could end up on one of the thin lines, which means it's on the plane of the paper or the plane of the screen. We have to be able to handle every one of these situations. All right, let's take a look first at the one that's considered the easiest of all, number 4 on the dash. So this is really just a repeat of what we already covered. Here's our 4 groups already assigned, and check it out. Number 4 is on the dash. So we said we check the travel of 1, 2, and 3. We ignore number 4. Here, 1, 2, and 3 appears to be going clockwise. It's going to the right. So we're going to call that letter R. R, right. Here's another example of the lowest group in the back. It's on the dash. All right, we check out the traveling direction of 1, 2, and 3. Here we see it's going to the left. It's going counterclockwise. We said that if 1, 2, and 3 is going counterclockwise, we're going to call that the S configuration. All right, now the next scenario that we are going to look at is when number 4 is on the wedge. This one is pretty straightforward too. Pretty much all we have to do is flip the letter. If number 4 ends up on the solid wedge like this, do what we just learned how to do, but then flip the letter inside out at the very end. So here, we're looking at the traveling direction of 1, 2, and 3. In this one, it's going to the right. It's going clockwise. So we would normally think of that as letter R, but because it's on the wedge, we have to flip this into the letter S. Let's look at another one. Number 4, solid wedge. We're going to do what we do. We look at the travel of 1, 2, and 3. In this case, it is going to the left. It's going counterclockwise. We think of that as S, but here, no, we have to flip it into letter R. The third way we're going to see number 4 is it could show up on the thin line. Now, being on the thin line just means it's on the plane of the screen or the plane of the paper. This is the one that causes the most student errors, so you got to really know what you're doing here. There's different ways to teach how to handle this. I'm going to show you a way that I think is really solid. I think you'll love it once you learn it. I'm hoping you'll love it. I use a idea from the Fisher projection to handle this. And if you've never heard of the Fisher projection, don't worry. I'm going to show you exactly what you need to know right now. Fisher projection is simply a way to show stereochemistry on a chiral center. And the way it works is we have a vertical spine, and then there's one or more horizontal arms that run through that vertical spine. The intersections represent carbons, and as you can see, this is a chiral center. It's got 4 different groups. Now, when we see a molecule written like this as a Fisher projection, it's actually implying that the stereochemistry looks like this. It's actually implying that the horizontal arms are coming forward while the vertical spine is going backwards. Now, I know this is a little bit unusual because we don't typically see our molecules looking like that, but the idea is that these horizontal arms are giving you a hug. They're coming forward, and the vertical is going back. So just to get an idea of what this might look like on a ball stick molecule, check it out. Here's a carbon in the middle. That's representing this. And see how the horizontals are projected forward? That's the hug. And then the vertical spine is going backwards. So just think of Fisher projection as a hug. But the main thing here is this idea of this alternating wedge, dash, wedge, dash. So the reason why I think this is important is because this gives us what I call the circle of alternation. The Fisher projection is communicating stereochemistry that actually looks like this. And the beauty of this alternating wedge dash, means that we can take any chiral center as presented and do this alternation. We can have a circle of alternation, if you will. Now, why is that important? Because now when we have this situation, number 4 is on the thin line, what we can do is apply the circle of alternation. Check out what's going on here. Here's number 4 on the thin line. This is where most students are going to have a hard time. But it doesn't have to be that way. We've got dash, wedge, dash. We're going to just follow the order of what's already presented. We're going to Fisherize our structure by applying what I'm calling the circle of alternation. And now we work off of this structure. See, number 4 is now a dash. And now that it's a dash, we just do what we normally do on a dash. So here's 1, 2, and 3 traveling clockwise to the right. We would just assign this the letter R. All right, so yeah, let's do another one of these. We check out our structure. Number 4 is on the thin line. Boo! But not boo, because we can just apply the circle of alternation. I look at what's already presented. We have a wedge, then a dash, then you go wedge. Wedge dash wedge. We're applying circle of alternation. There it is. Number 4 is on the wedge now. Okay, no problem. We just do what we learned when number 4 is on the wedge. This is traveling to the left, counterclockwise. Normally we would call that letter S, but we're going to flip that into letter R in this case. All right, so let's just do the final recap of what we do for assigning R and S when we know all the assignments. 3 situations. Number 4 can be on the dash. That is the traditional view. If 1, 2, and 3 is going clockwise, we're going to call it R. If 1, 2, and 3 is going counterclockwise to the left, we're going to call that S. So what's going on here? 1, 2, and 3 is going to the left, so that would be an S. Here's the next situation. The lowest priority group is coming at us on the wedge. All right, that's where we do the opposite. We do what we did over here, but then flip the letter. So here is a 1, 2, and 3, again, looking like it's traveling to the left, like an S, but we're going to flip that into an R. And then finally, on circle of alternation, when we have the lowest priority group on the thin line, what we would do is we would say, here's dash, here's solid. This would become a dash. A dash. So we would do what we do over here. In this event, 1, 2, and 3 is traveling clockwise. So we would end up calling this letter R. All right, so we just went through what to do when we have the 1, 2, 3, and 4. The last part of this is to actually learn how to systematically assign the 1, 2, 3, and 4 to the groups. So we're going to do that right now in some actual molecules, and we're going to be doing R and S in its full capacity. Okay, we've come to the last part of what we have to learn how to do. We're about to learn how to assign the actual 1, 2, 3, and 4 to the 4 different groups. So I've got 6 molecules for us to work on. Each of these molecules illustrates something important that you're going to have to be learning how to handle. So without further ado, let's just dive right into it. Right here is our first structure, and this of course is showcasing the most straightforward type of question you're going to get. When we assign RNS, the way it works is we go to our chiral center. So that's right here. We got our 4 different groups attached to the carbon. And here's how it works. We look at the atom that is attached to the chiral center. We look at the first atom in every direction because we're going to be doing this by making the highest atomic number the highest priority and the lowest atomic number the lowest priority. So again, this system is based on atomic number. Number, not weight. More about that later. So check it out. We've got bromine, carbon, hydrogen, and chlorine. Okay, 4 different groups. That is the easiest situation to handle. We just start assigning priorities based on highest number. Bromine is the highest atomic number of these 4, so this ends up being priority 1. Chlorine is our second highest atomic number. That's going to be priority 2. Carbon will be our third. And then hydrogen will be our 4th. So it is a good awareness that if you have a hydrogen on the chiral center, that's going to be your lowest priority group. That being said, not every chiral center has a hydrogen on it. So you can't just say, oh, it's got to be hydrogen. Or, Eddie, there's no hydrogen on the chiral center. How do I solve this? No, you got to look for atomic number. All right, so now what do we have? We got our lowest priority group on the dash. So you know what to do. We look at the traveling direction of 1, 2, and 3. Here it is going to the left. It's going counterclockwise. So what do we have? S. Okay, moving on to our next example. This time we don't have 4 different atoms touching the chiral center. Check it out. Here's our middle carbon, our chiral carbon. We have a methyl here and an ethyl here. Now, it's important to realize that even though they're both carbons that are touching that middle carbon, that chiral carbon, the substituent as a whole is not identical, meaning a carbon with 3 hydrogens, methyl, is not exactly the same as a carbon with 2 hydrogens and then another carbon, ethyl. So these count as 2 different groups. What do we do now? All right, we still do the rule of look at the atom that is directly touching the chiral center. Carbon, hydrogen, oxygen, and carbon. All right, so we can at least say that hydrogen is going to be our lowest priority. So there's our number 4. And we can say that the oxygen is going to be our highest priority. So that's going to be our number 1. But how do we sort it out between these 2 carbons? What we have to do when you have a tie is you now look at the next 3 groups that are attached. So we always work by moving away from the chiral center. So what I mean by that is, here's a methyl. Because this carbon is touching 3 hydrogens, it would be shooting out to hydrogen, hydrogen, and hydrogen. So I look at that and I say the trio of attachments on that carbon is hydrogen, hydrogen, and hydrogen. Over here, this carbon is touching 2 hydrogens, but then it touches a carbon. We got hydrogen, hydrogen, and carbon. So now I think of that as a trio of carbon, hydrogen, and hydrogen. I list the 3 atoms that are coming out of that carbon. I like to list them in descending atomic number because it makes it easy for us to do what has to be done next. We're going to be comparing the highest priority attachment out of who's coming out of this carbon against the highest priority attachment coming out of this carbon. Well, coming out of here, it would be the carbon, but then coming out of here, it's only hydrogen. So the fact that you have a carbon being a higher atomic number than a hydrogen, that's going to mean that this ethyl group is the highest priority. So now we know ethyl is going to be our number 2, and methyl is our 3. We have our 4 groups assigned. Now we do what we learned before. Our hydrogen, our lowest group, is on the wedge, so we're going to be flipping our letter. We look at the direction of travel of the 1, 2, 3. Here, it's going to the right. It's going clockwise. Normally, we would call that R, but no, we're going to flip this into S. So let's now take a look at, again, a scenario where we have the carbon touching the same atom more than once. of course, we can have multiple chiral centers on our structures. Now, in this case, it might kind of look like there might be 2 chiral centers, but don't be fooled. Check it out. This carbon up here, even though it's showing wedges and dashes, is not a chiral center. Why? Because it's got 2 of the same groups. It's got 2 methyls. So don't be fooled. Over here, though, yes, we have 4 different groups. We got a oxygen, a methyl, a neighbor ring carbon with 2 carbons coming out of it, and a neighbor ring carbon that does not have 2 carbons coming out. So there's our 4 different groups. So again, we go by atomic number. Who is directly attached to the chiral center? Well, here we go. We look in all 4 directions. We got carbon down there, carbon right there, another carbon, and oxygen. Okay, so we can at least say oxygen's the highest atomic number there, so that is priority number 1. Now we're going to look at the 3 carbons and sort out their trio of attachments. Okay, methyl is always a dog. You know, it's got 3 hydrogens. So for the most part, methyl's going to lose to other carbons. So this thing here has its 3 hydrogens coming out. It's, let's call it its subset of attachments, 3 H's. How about here? This, and again, we keep working away from the chiral center. Here, we go carbon, carbon, carbon. Not bad, 3 carbons. All right, and then what about down here? This goes to carbon, and then the hidden implied hydrogen, hydrogen. So we are going to have a CHH on that carbon. Now we look at the best of every one of the attachments. Again, methyl, the best it does is goes off to a hydrogen. So that right away loses to both of the other carbons because both of the other carbons' best attachment is another carbon. So methyl just became our lowest priority group, our number 4. So here's a good example of we don't always have hydrogen representing the lowest priority group. And then sorting it out between this arm and this arm, we've got the situation where this carbon we said is CCC. This is going to CHH. So at the second position, this is a C, where the best this down here is an H. That means that this arm is higher priority. This is our number 2. So we've got our 3 down here, our 2 here, and our 4 here. So check it out. Number 4 is on the wedge. We're going to be flip-flopping the final letter. Check the traveling direction of 1, 2, and 3. Looks like it is going leftwards, counterclockwise, like an S. So we got to flip that into an R. Now, the next situation I wanted to take a look at is how do we handle it when there's pi bonds coming out of the atom? Of course, this is something you're going to be encountering, and yes, this can be tricky for students sometimes. I will show you. All right, we've got our chiral carbon right here. This thing is going to a carbon that's triple bonded to nitrogen. It's going to another carbon that's part of a carbonyl. It's going to this carbon who is an alkene. And then don't forget who's in there, an implied dashed hydrogen. So we actually have a dashed hydrogen. I'm going to draw that in. Okay, so we do what we've been saying. Look at the first atom in every direction. Carbon, hydrogen, carbon, and carbon. Okay, so at least hydrogen can be given the lowest priority, the number 4. Now, how do we do this with the pi bonds? We count a pi bond as an attachment to whatever atom it's attached to. So for example, this carbon is triple bonded to nitrogen. So we look at that as though it's a carbon bonded to nitrogen, nitrogen, and nitrogen. Three nitrogens, because it's got 3 lines. How about here? This carbon is going to oxygen, oxygen. It's a double bond to oxygen, so we count it as 2 oxygens. And a carbon. And then what about down here? This carbon, don't forget, there's a hydrogen. There's a hydrogen coming out of here. So this is going to carbon, carbon, hydrogen. So the trio there is CCH. All right, we can start giving out priorities. The best priority coming out of this carbon is oxygen. That is a higher atomic number than the nitrogen. So as far as it goes for assigning priorities, this arm to the carbon with oxygen on it is 1. This arm to the carbon touching nitrogen is 2. And then this arm, the carbon going to other carbons, is going to be our 3. So we have our 1, 2, 3, and 4 all set up on the structure. Lowest priority group is on the dash. Great. So what do we have here? R or S? Well, we check the traveling direction. 1, 2, 3 is going to the right, going clockwise. So it's going to be letter R. Moving along, another example of pi bonds. Now, of course, this one's a little bit trickier. Looking here, we're looking for chiral centers. Aha, right there. That's the only one. Remember, you don't want to say sp2 atoms are chiral centers. So don't go here and say, oh, hey, how about this carbon? No, that's a double bonded carbon. We're not calling those chiral centers. This is not chiral because there's 2 methyls. But this is. Now, once again, we have the situation of a hidden implied hydrogen. And it's going to be on the dash. So yeah, let me, again, draw that in for us. We know it's a dash because if you have this exact situation where only one of the substituents is shown as a wedge or a dash, and you got to draw in a hidden implied hydrogen, you have to assume that the hydrogen is the opposite. The opposite. Okay, so let's start taking a look at what to do. Neighbor here, carbon, 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 hydrogen. All right, so hydrogen's our lowest. Hydrogen's our number 4. How about the other 3? Well, let's say this carbon's going out to carbon, carbon, and then the hidden hydrogen. So it's a CCH. What about here? This is going to a carbon, hydrogen, and hydrogen, the hidden implied hydrogens. So this is CHH. What about down here? Okay, so this is going carbon, carbon, hydrogen. As we said, if it's a pi bond, you're going to count it as 2 attachments to whatever comes next. So if this is CCH, and if this is CCH, and this is CHH, we at least know that this arm becomes number 3. Okay, that's number 3. But how do we sort it out now between these two? We got to now do a thing where often there's confusion. It's a total tie. This is saying CCH. This is saying CCH. You take the best carbon on this arm against the best carbon off this arm. Now, because both of these carbons are methyl, all right, you're going to be working with methyl. You're going to be working with this carbon who's going to HHH. All right, so you can see this is already not good. But how do we do this? We said that this went to CCH, and now we said we're supposed to go to the next carbon and figure out like what it's attached to. What we do on the double bond like this, we go out here. We do go out here. And now here's where you got to be careful. I know I've been saying that we always work away from the chiral center, but when you have a pi bond like this, you actually double back once. We look at this and we say, this carbon is going off to carbon. We go back. On a pi bond, we go back one time. This is going to carbon, carbon, and hydrogen. So that's going to be higher priority. This here that we just said is going to carbon, carbon, and hydrogen is a higher priority than this carbon is going to hydrogen, hydrogen, hydrogen. Again, we're doing it by atomic number. So now we can say that we have our hydrogen was 4. We said this arm was 3. This arm to the isopropyl is our 2, and this is our 1. So we have our low group on the dash. Excellent. 1, 2, 3 clockwise, R. All right, now this pi bond example is a little bit trickier than what we just did. We're checking out where's the chiral centers. Only right there. See, even though that's got 4 groups coming out, it's got 2 methyls, so it's not chiral. Right here, we got 4 different groups. So we're doing what we do. We look at the atoms in every direction. Carbon, 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 and hydrogen. All right, so at least we have hydrogen clearly spelled out for us as our lowest, number 4. Now what? Well, this carbon is going out to HHH. It's methyl. Remember, we said methyl loses to other carbons. So let's just give that number 3 right now. And now we're going to figure it out between these 2 carbons. So coming down here, this is going out to carbon, carbon, carbon. Okay, so 3 carbons. How about this? This is going to carbon, carbon, and carbon. So again, a tie. this and this are both going to 3 carbons. So remember what we said. We now take the best of each substituent against each other. This one here, the best carbon attachment is this one because it's an ethyl. It keeps going on to more carbon. Where this is just the 2 crummy methyls. It stops at hydrogens. So we are going to compare this carbon. And then what do we do here? Now, here's what you got to watch out. Is this carbon better or is this carbon better? This carbon goes off to hydrogen, hydrogen, and hydrogen. This carbon here goes to carbon, hydrogen, and hydrogen. So it is this carbon that is better. So we're now looking at carbon, hydrogen, and hydrogen up against carbon, hydrogen, and hydrogen. So it's still not settled. It's still not settled. Again, if we're here, this is going carbon and then the 2 hydrogens, hydrogen, hydrogen. We're comparing that to this carbon. Carbon, hydrogen, hydrogen. Now what? Okay, we got to go to the next best substituent. Well, here it's this carbon. Now, this is where you got to be careful because I know I said, oh, methyl always loses. But this carbon here keeps on rolling out to hydrogen, hydrogen, and hydrogen. Here's the trick. We said you only go out one time on a pi bond. So we already went out. When we said, hey, this was going to carbon H and H, that was the end of the road. We don't go back and start saying, okay, well, hey, now we're looking at this carbon going back to these guys. No. We basically ran out of stuff for this carbon to go to. So in this case, this arm is higher priority than this arm. So now we can put our four priorities on. We've got our 1, 2, 3, and 4 in place now. And lowest priority group is in the back. So 1, 2, and 3 is traveling to the right, clockwise, letter R. All right, now finally, I wanted to take a look at one molecule that could easily be misleading a student into the thing I said about the weight of the substituent. How many times I've seen students get messed up on stuff like this. Here's our chiral center, and we start taking a look at this, and the student says, okay, yeah, carbon, 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 everybody's carbon. Whoa, oh my gosh, look at this huge structure. Look at all these bromines. You know, bromine is definitely the highest atomic number on that entire structure. So the student just says that right there is it must be the priority. No, we have to be systematic. Remember, carbon, methyl, Me is CH3 is carbon. Here's another carbon, and here's a carbon. All right, so they're all four of these are carbons. Who is the best single attachment? This is another way I sometimes do this. Instead of just always writing the subset of 3, sometimes I just say, who's the best single attachment coming out of the carbon? All right, well, let's check it out. The best direct attachment coming off here is oxygen. The best direct attachment coming out of this is another carbon. Here's methyl. The best coming out of here is hydrogen. And then, ooh, the best coming out of here is a fluorine. Don't get fooled. Look at that. There's a fluorine. Fluorine is the highest atomic number when we're comparing fluorine, hydrogens, carbons, and oxygens. So what does that mean? That means that right here, this is our priority 1. This arm to the oxygen is our 2. This one going out to carbons will be 3. And then here, we're going to have our number 4. Methyl will be our 4. All right, so again, let's do R and S. We've got our lowest group on the wedge this time, so we got to flip that thing inside out. We look at the travel of 1, 2, 3. It's going clockwise. 1, 2, and 3 is going clockwise, so usually we call it R, but we got to flip it into S because it is on the wedge. All right, so we've pretty much gone through everything we got to do as far as learning how to assign the priorities, how to deal with R and S no matter where number 4 is. The next thing you got to do is practice. You have to do practice problems on this. One of the things that will ensure your success in this class is if you can do R and S very quickly. Because, I mean, of course, you're going to get questions that just ask you to do R and S, but there's a lot of things. There's a lot of things in this class that rely on you being able to understand if something's R or S for your success. So go and practice